Hello everyone, welcome to the 16th lecture of this course. So in our previous lesson we have seen how the beam design is being performed in STAAD Pro for the gravity loads. We have also understood the design parameters and also the design output given in the STAAD analysis output, right? So today we will continue with the column design part for the gravity loads, and we will see the design output. We will try to understand how the design output is being arranged, and we will also see different other commands that we need to assign while performing the column design. Okay, so let's get started. So first of all, I will open the analysis output from utilities. The structure is already analyzed and designed, so I will go to analysis output. So here you can see the analysis output, and I'll directly go to the column design. So I'll just click on this column design, and here let's begin with this first column. So here the first column is the column number 21. So what are the data that are given? The grade of concrete as usual, which was given for the beam also. These are the inputs that we have given. Fe 500 grade for the main reinforcement and Fe 415 for the stirrups that we have assigned, right? So here you can see the length of the column. It is 2500. So here this length is nothing but the center to center distance, or you can say node to node distance. Okay, so sorry, not center to center, node to node distance. Let me draw it here actually. So suppose you have a column like this, and you have also beam here, right? So what we have modeled, actually we have modeled this point actually. We have modeled this point, right, like this. So this distance is given here as 2500. So this is the total node to node distance. Okay, so this total node to node distance is 2500. Here you can see the cross section that we have used. It was of 300 by 300. Okay, cross section we have used, and the cover to the main reinforcement, again the cover we have assigned is 40 mm. So these are the correct inputs that we can see here. Now let's begin with the design results. So first of all what is given is the design axial force PU. So it is 834.25. fine. So this is my PU. Initial moments. Okay, so that means MUZ. Okay, moment about Z axis. So suppose this is my column. Okay, this is my column. So if I just draw the, you can say, axis, so it will be something like this. Suppose Z, and suppose this is my Y axis. So these are the local axis actually. Okay, these are the local axis that I am drawing. This is my X axis. So now here it is giving that about Z axis, about this axis. So this is my MUZ. Okay, so it is 8.76, and about Y axis, okay, maybe it can be in other direction also. So if I just put the thumb like this, so yeah, it will be in this direction only if it is positive. Okay, if you put your thumb in this direction, whatever the direction of your other fingers, like the other fingers will be bent, right? So what are the directions of your other fingers will define the direction of your movements. If it is negative, then it will be the opposite direction. Okay, in that case maybe it will be in this direction. Okay, so as the moments value as positive, so that we will see later, that I have already discussed also. So now the thing is that we have got the you can say biaxial moments, 8.76 you can say kilonewton meter. Obviously you can see the you can say unit here, and 5.47 kilonewton meter. Okay, Now we have moments due to minimum eccentricity. So do you remember that we have also checked the minimum eccentricity, which was E equal to it was L unsupported, okay, L unsupported length of the column divided by 500 plus D by 30, D or B it will be, okay. So means the dimension by 30, and the eccentricity moment, so you can say mu due to eccentricity, it will be pu multiplied by my eccentricity, whatever eccentricity I am considering, okay. So now for this we also know that the minimum eccentricity, whatever value we have got, suppose it is some value of 14, so whatever value we are getting, we need to compare with another value which is 20. So whichever is greater, okay, that we need to consider. If it is less than 20, then we need to consider the eccentricity, sorry, not this one actually, not this value, I'm talking about this value, okay. So whatever value we got, we need to compare it with 20 mm, whichever is greater. So that we need to consider as our eccentricity, minimum eccentricity, and then we need to find out the moment due to minimum eccentricity, okay. So here, if you see here, what is the moment due to minimum eccentricity? 16.69. So let us check how it is being found actually. So here by default, whenever we are checking the minimum eccentricity, the STAAD will consider the unsupported length as the node to node distance of the column, okay. So the node to node length is nothing but 2500. So if you just calculate like this, so 2500 by you can say 500 plus, now as it is in both direction we have 300 mm, okay. So about z axis, suppose about this axis, then also we are having same 300. About y axis, that also we have 300 mm. So I will give 300 by 30. So how much we are getting? So if you just find out 2500 divided by 500 plus 300 by 30, so a value of 15 we are getting, which is less than 20, okay, which is less than 20. So we will be considering, hence we will be considering E is equal to 20 mm. So what will be moment due to eccentricity? So this factored pu value we got, right? So pu into E, okay. So how much it will be? How much it will be? Mu due to eccentricity, how much it will be? It will be, you can see 834.5 multiplied by 0.02, right, is as it is in kilonewton meter. So how much we will be getting? 834.5 multiplied by 0.02, so we are getting a value of 16.69 kilonewton meter. This is what you can see here. 16.69 is defined in both directions. Now the problem here is that the code says we need to check with the L unsupported, but the software it is actually calculating, though we have considered 20 mm, but in some cases you will see that this value, that the calculated eccentricity value, is higher than the eccentricity of 20 mm. So in that case, for this calculation it is not an issue, because anyway we are taking 20 mm, right? But whenever this value is greater than 20 mm, so in that case this you can say unsupported length that need to be provided correctly, otherwise we may be overestimating this particular thing, right? So for this, what we need to do, basically, in general process, whenever we are doing the building design, so you may ignore this as it is overestimating, so you may say that we are in the conservative side, but as I'm explaining the concept behind it, so I'll be showing you how we can do that actually. So to define the unsupported length of the columns, so in that case, what we need to do, we need to assign two commands, which are uly and ulz. So these are called unsupported length ratios. Unsupported length ratios. Okay, these we need to you can say assign. So unsupported length ratio means ratio of unsupported length. So it is L unsupported by actual length. Okay, so this is the unsupported length ratio we need to assign. One more thing, you will be seeing that here this unsupported length, the moment due to minimum eccentricity is calculated for both the axes. Okay, but for this reason, what I will do, I will just open the code and I will show you what code says about it. So if you just see this clause 25.4 minimum eccentricity, it is saying that all columns shall be designed for minimum eccentricity equal to the unsupported length of column by 500 plus lateral dimensions by 30, which we have already seen, subject to minimum of 20 mm. So this thing we have done, where biaxial bending is considered. So whenever we have biaxial bending in the column, it is sufficient to ensure that eccentricity exceeds the minimum about one axis at a time. Okay, so whenever we have biaxial bending, in that case, whichever is greater in between two axes, so we may consider only that one value, and we can go we can say proceed with the calculation. Okay, so that means in that case only one axis, like we'll be checking both the axes, and whatever is higher we'll be considering that. Okay, so it says that whichever is you can see it is sufficient to ensure eccentricity exceeds the minimum, means whatever eccentricity we are getting, if it is exceeding the minimum eccentricity about one axis at a time. Okay, so in that case there will be another you can say command that I will be showing you. So as we were discussing about this you can say column number 21, so what I will do, let me see which one is column number 21. So I will just turn on the beam numbers by pressing Shift B. So you can see the beam numbers here. So here we have the column number 21, the bottom story. Okay, and here we have the two beams. So what I will do, I'll just select this beam and this column, right click and new view. Okay, so here you can see. Okay, so now if you just see, let me turn on the labels for this. Okay, so this is the column number 21, and let me change the colors so that beams, maybe I'll change something light color. Or okay, okay, so now this is clearly visible. You can see the beams and columns. So now let me also turn on the local axis. So for this, Shift O. Okay, the local axis, I think it will not be visible in case of extruded view. Let me see how we can change it. There was a command to change this view actually to wireframe. I just forgot section outline actually. Yes, now it is better. Okay, so I just forgot the shortcut actually. If you remember, please do use it. Otherwise I will tell you in the next class. So there is a shortcut to change these views, okay, from solid to single line or from wireframe to single line. So here if you see that the total length from node to node is given from this node to this node, which is of 2500. Okay, so now what we have to do, we have to find out the unsupported length factors. So remember here, see, for, so this is my y-axis, this is my z-axis, and this is my x-axis. Okay, so unsupported length along, first of all we'll be finding out unsupported length of the column along y-axis. So this is my along y-axis and this is my along z-axis. Okay, so unsupported length along y-axis, how will you finding out? This depth of the beam, we know that it is 750 mm. Okay, so unsupported length along y-axis, it will be, sorry, let me, should not write like this, like I should write this L unsupported along y-axis. Okay, so it will be how much? It will be 2500 minus 750. Okay, this is 750 mm. Fine. So how much we are getting? We are getting 1750 mm. Fine. And unsupported length about z-axis, how much we are getting? So this depth we know it is 500 mm. So I just want to calculate this distance. So how much it will be? 2500 minus 500, so it will be 2000 mm, right? So L unsupported along z-axis, it will be 2500 minus 2000, so it will be 500, sorry, not 2000, minus 500, so we'll be getting 2000 mm. Fine. Now when we will be assigning the ULY and ULZ, so these are actually unsupported lengths about the axis. Okay, or unsupported length factor about the axis. So now it is pretty critical actually, we need to understand it properly. So unsupported length about y-axis length factor. So about y-axis, which unsupported length we are going to get? So about y-axis, we are going to get the unsupported length, which is 2000 mm, right? Because in this case, it will be, the column is bending like this. Okay, so which length will be getting? It is 2000 mm. So in case of ULY, okay, unsupported length factor about y-axis, it will be 2000 divided by 2500, which is how much? So 2000 divided by 2500, we are getting 0.8. Okay, and unsupported length about z-axis. So about z-axis, when we'll be doing about z-axis, which length will be effective here? Which length will be effective here? So in that case, this particular length will be effective, which is of 1750, right? Because in that case, the column will be bending from face of this beam, like not bending from face actually. There will be some more distance as we'll be finding out the effective length. But for now, we are considering that it will be like this. Okay, as we have restrained up to here. Obviously it will not happen like this actually. Obviously it will be starting like this, so we will get some more length. So that's why we calculate the effective length basically, which I have already explained in the column design manual regulation, right? So here the effective unsupported length will be 1750. So ULZ will be 1750 divided by 2500. So how much it will be? 1750 divided by 2500. So it will be 0.7. Okay, so this ULZ ULY parameter we need to assign in the I can say this design parameters, so that the software can calculate the you can say minimum eccentricity moment properly. Okay, here in these commands I will be assigning those you can say commands actually. So suppose anywhere before the design command actually need to find you need to apply. So suppose after this I will be you can say providing those commands. So I'll just go to or you can provide before the design of column also. Okay, so before after beam design also you can assign those, your wish, but it needs to be before the design of column. Okay, so maybe we will assign after this beam design. So I'll just go to define parameter. I'll go to ULY, and ULY we have considered 0.8, right? ULY we have considered 0.8 2000, yes. And I'll click on this after current, so that it will be adding after beam design, add current and add, and ULZ we are assigning 0.7 after current, add. There is one more you can say command that we will be assigning, which is this method. So you can see, consider minimum eccentricity about one axis at a time as per clause 25.4 of IS 456-2000. So this method 1 will be applying here. So after current, add. Okay, so let us select this column and let us assign this. So ULY, select this column, assign to selected column, selected beams, assign. ULZ, I'll select this, assign to selected beams, assign. Method 1, select this, assign to selected beams, assign. Yes. Okay, so now it is assigned. Okay, let us run the analysis again. Analysis, and let me close this actually and run the analysis again. Save. Okay, fine. So now if I go to view output, done. So here again, let's go to column design. Now you can see here that about y-axis we are getting the minimum eccentricity 16.69, the same value, because now also if we calculate that what is the you can say minimum eccentricity, actual minimum eccentricity which we're going to calculate will be less than this value, right? So obviously it will be taking the minimum eccentricity considering 20 mm eccentricity, right? So but now it is not calculating for both the axes. Okay, so whichever is greater, it is creating this one 16.69. okay, and for the other axis it is keeping it 0. Fine. So now when we are going to find out the final moment, whichever is greater between the initial moment and the minimum eccentricity, we'll be considering that. Okay, so now here the slenderness ratio we all know, L effective by depth. Now again we have not assigned any L effective value, but whenever we are is analyzing with the default parameters, in that case STAAD will be considering the effective length as the node to node distance of the column. Okay, means the node to node length. So this L effective, basically why we are keeping it as 1, because now we have only designing, or you can say analyzing the structure for the gravity load. So if you see the code, let me just minimize this. If you just see the code, and if I take you to the NX E, most probably, yes, here. So as we are designing the structure for dead load and live load, gravity loads, we are considering the structure has no sway. So in no sway condition, the maximum value of unsupported length, sorry, effective length ratio we can get as 1. Okay, so considering that we are here in STAAD.Pro also, we are not applying any further value as we are designing only for gravity loads now. But when we'll be designing for lateral loads, as I have explained earlier, you need to you can say find out the effective length, okay, as per this NXE, that I will be explaining again actually how you can do that. And you need to see whether the frame is sway or no sway, okay, and as accordingly you need to find out the effective length ratio. If it is no sway, conservatively we can take directly 1. Okay, if it is sway, then we need to see which value we need to take from here. Okay, because you can see it is up to infinite, so that means whenever you getting any value which is infinite, that means your structure is not stable at all. Okay, so that's why in that case we cannot provide the maximum value. We need to calculate it properly and to assign it. There are some industry practices that also I'll explain actually, because this particular process of finding the K or effective length ratio is very difficult. Some softwares are capable of doing it automatically, but unfortunately STAAD.Pro is not capable. So in that case, what we need to do, we need to calculate by ourselves. But in complex structures, it is very hard also to calculate for every single column actually. So we will see what are the different industry practices being followed in such cases. Okay, so now if I just go back to the design output, so standardness ratio L effective by D actually. So here if you see, the D is 300 in both the cases. L effective, as we are taking the effective length ratio as 1, so the L effective here it will be 2500 divided by 300 for both the axes. So how much it will be? So we'll be getting 2500 divided by 300, so we are getting 8.33, which is less than 12. So we can say that our column is not a slender column. If it is a slender column, in that case this additional moment will be calculated, okay, as we have seen earlier, right? So this additional moment will be calculated, and then among these two, whichever is greater, it will be taken here. So you can see it is taken, plus this additional moment will be added here. Okay, so here also among these two, the 16.69 is greater, so it is taken. As there is no additional moment, so it is not added. If it is there due to you can say slenderness effect, so in that case it will be added here. Fine. So now moment reduction factors, this is also there whenever we have the slenderness. You can say, let me take you to the clause so that you can have a clear idea of it. So let me minimize it. Let me go to there itself. Yeah, here you can see here the values given. So this is the additional moment that we are getting whenever we have the slenderness effect. Now if you see 39.7.1.1, it says the values given by equation 39.7.1 may be multiplied by a following factor K. Okay, so this K we can find out using PUZ minus PU. So this is already I have explained how we need to find out the PUZ, and I have not explained actually how we need to find out this PB. So this value PB we can get from SP16 actually, and you can see the axial load corresponding to the condition of maximum compressive strain of 0.0035 in concrete and tensile strain of 0.002 in outermost layer of tensile steel. So this is actually we'll be taking from SP16. So later on I'll be explaining you this also, but if you want you can say avoid using this. But software, if you design using software, so in that case the software will be using this whenever you are calculating the additional moment. Okay, it will be calculating the reduction factor automatically, and it will, you can say, reduce the additional moment, and finally you will be getting the additional moment from in here. Okay, as we are not getting any additional moment or slenderness effect, so these things are not calculated now. Okay, so finally we have got the moment and the PU. Okay, so biaxial moments and pu, that means the axial force. Now this required steel is you can say calculated, and this is the interaction ratio 0.29. so how this interaction ratio is being calculated? So this is calculated as per this. You can see here, moment capacity by required, you can say, what is the analysis moment. Okay, sorry, analysis moment by moment capacity about that axis to the power alpha n. You know how we have found out the alpha n using this. Okay, we need to find out the pu z value, and based on the pu by pu z, we'll be choosing whether it is 0.2 or 0.8 or in between any value, right? So again, then by adding both of this, okay, moment demand by moment capacity about one axis to the power alpha n, plus again the same for the other axis, this interaction should be less than 1. Okay, so what we are getting here, so this you can see, this interaction ratio we are getting 0.25. okay, so that means the column size we are given for this particular you can say column, it is very, you can say, higher, you can say. Okay, otherwise the interaction ratio may be coming as 0.5, 0.8. so when the value is 0.5, 0.8, in that case you can say that the column is designed economically. Otherwise maybe the steel is provided higher, or the section we have taken is very high in terms of the demand of moment and axial force. Okay, so as per clause 39.6, you can see, so this is what 39.6 is telling us, right? Okay, so this interaction is being calculated, and then here the STAAD is giving us the interaction ratio here. Okay, so the steel required is 598.57 square mm based on this interaction. Okay, it is very high, or the section is very high, which is not required actually. Okay, so we can work out this later. Now we can see here required steel area in 4 cases. Okay, we have got 2 case in joint number 1 and 2 case in joint number 6. so among these 4 cases, the critical one, the critical reinforcement requirement, we have got 598.57. so you can check once again, we must cross check whatever we are getting. Actually it is 592.86, 592.86, in the other case 598.57, and obviously it will be also same 598.57. so 598.57 is the required steel area. Required concrete area, so this one, fine. Main reinforcement provided 16 mm dia bar, and here you can see from the percentage of reinforcement, you can see that in that case what we can do, the force is so low that we may reduce the column size, but obviously we will not reduce the column size from 300 to 300. so we can go with this particular percentage of reinforcement. But one problem with STAAD Pro, I will say you that in many cases you will see that STAAD is providing percentage of reinforcement less than 0.8%. remember, in such cases you should not provide reinforcement less than 0.8%, because the minimum percentage of reinforcement to be provided in column as per IS 456 is 0.8%. so if the STAAD is giving you any result which is less than 0.8%, you should not consider that, and you should you can say calculate, or you should assume a reinforcement which is greater than or equal to 0.8%. okay, and accordingly you need to find out the area of reinforcement. So as we have considered the equally distributed, so it is also written that equally distributed. And the usual process of shear reinforcement design, as we have seen in the beam also, so the usual process of shear reinforcement design is you can say considered. And then after this, the spacing criterias and all, let us check. If I just go to page number columns, so here the spacing criterias, percentage of reinforcement, everything you will be getting here. So you can see here, one line by, you need to read this. So the cross-sectional area of longitudinal reinforcement shall not be less than 0.8%. Here you can see how clearly it is written. It should not be less than 0.8%. Even if it is coming that 0.8% is enough, or less than 0.8% is enough, we should provide at least 0.8% in the column. And what is the maximum percentage of reinforcement? It is 6%, but we hardly go beyond 3%. In major structures maybe 4%, but you should not go more than that. In that case it will be uneconomical, or maybe it will be also a problem for in terms of execution. Okay, so you can see here 6% is the maximum that we can allow as per the code. So it is a theoretical approach. Practically we should not go beyond this even in the major structures. In small structures we always you can say try to keep the reinforcement percentage within 2%. Okay, or in some people also go up to 3%. Okay, so now let us again read this. So you can see the use of 6% reinforcement may involve practical difficulties in placing and compacting of concrete, as I said now. Hence, a lower percentage is recommended, where bars from the columns below have to be lapped with those in the column under consideration, and the percentage of steel shall not usually exceed 4%, as I said. Okay, so we should not go beyond 4% actually. In any column that has larger cross-sectional area than that required to support the load, the minimum percentage of steel shall be based upon the area of concrete required to resist the direct stress, not upon the actual area. Okay, so that means it says that whenever we are providing, suppose the concrete area that is required, okay, AC that is required, so it is much greater, like whatever we have calculated the required, I can say area of concrete, it is much greater than the demand. Okay, much greater than the area demand. So in that case, when you will be finding out the minimum percentage of reinforcement, 0.8%, this 0.8% should be of the area which is required, not of which you have provided. Okay, this it is actually meant to say that whenever you are providing minimum reinforcement, if the area of concrete you have given much more than the required area, in that case the percentage of reinforcement should be based on the area which is actually required. Fine. So then again, minimum number of bars, longitudinal bars provided in column shall be 4 in rectangular columns and 6 in circular columns. So whenever you have 4 rectangular columns, so at least 4 bars you need to provide, and whenever you are designing for circular columns, so at least 6 bars you need to provide. Okay, 5, 6. Okay, 6 bars you need to provide. The bar shall not be less than 12 mm. So we cannot use any bar which is less than 12 mm. Actually, we do not use 12 mm also. We start using from 16 mm in general. Okay, and then we have the reinforced concrete column having helical reinforcement shall have at least 6 bars of longitudinal reinforcement within the helical reinforcement. See, helical reinforcement we do not provide actually, unless or until it is a circular column. Even in the circular column also we are not provide. Nowadays this practice of providing helical reinforcement means the stirrups are gone actually. So it says if you have helical reinforcement like this, so in that case the main bar should be at least 6, which we are totally avoiding nowadays. So no use of this clause. In helically reinforced column, the longitudinal bar shall be in contact with helical reinforcement and equidistant around its inner circumference. So let's avoid this. We are not going with this actually now. Then we have spacing of longitudinal bars measured along the periphery of the column shall not exceed 300 mm. So this spacing that we are providing, suppose we are providing 3 bars, this spacing of longitudinal bars should not exceed 300 mm. It should not be you can say more than 300 mm. Okay, minimum of in case of pedestals, which the longitudinal reinforcement is not taken into account in strength calculation, nominal longitudinal reinforcement not less than 0.15% of the cross-sectional area shall be provided. So this is actually in case of pedestals. So pedestals, first of all, we need to see some definition of pedestal. So you can see the definition of pedestal is given here. Pedestal is a compression member, the effective length of which does not exceed 3 times the least lateral dimension. Okay, so effective length of this L effective should not more than D or B by, sorry, not D actually, B by how much? Does not exceed 3 times. Okay, so it will be 3B. Okay, if the L effective is not greater than 3B, in that case we can consider that column as a you can say pedestal. So where we use pedestals, in case of steel structures, if you see, we used to have, you can say, suppose a box section, and then we'll be providing base plate. Okay, and then suppose this is my ground level, this is my ground level. So from here we will be having like this pedestal, RCC pedestal, which will go beyond the ground and it will be connected with the footing here. Okay, so that you can say steel column will be rested on the RCC pedestal. So in such cases we use pedestal. So whenever you are designing the pedestal, it is the same process, same column design process, but in such cases the pedestal, how we'll be defining the pedestal is actually L effective should not greater than 3 times the least dimension of the column. So that's why I have written 3B. Okay, so in such cases this particular clause is applicable, this clause H, that in case of pedestals in which the longitudinal reinforcement is not taken in account in strength calculation. Suppose there is no required of longitudinal reinforcement, the concrete that we have provided is itself is enough. So in such cases what we will do, we will only provide minimum percentage of reinforcement. So in such cases we will not provide 0.8%, we will be providing 0.15% of you can say reinforcement, 0.15% of the cross-sectional area. Okay, so but again, if the demand is more, that means the whatever is the moment capacity of the section, if the analysis moment is higher than that, so obviously in that case the reinforcement will be calculating based on the demand. Okay, not the minimum reinforcement. But this clause is only when the moment capacity of the section is enough to take that moment, analysis moment. So in that case only 0.15% of minimum reinforcement will be providing in the pedestal. Okay, so this is what it meant to say actually. So these are the clause that we need to read properly. Again, we have the transverse reinforcement also. Here you can see the transverse reinforcement criteria for the transverse reinforcement is given in 26.5.3.2. This particular thing also, it is a matter of understanding. We need to understand these diagrams. So what I will do, I will take up this particular part in the next section. So today we will keep up to this only. In the next session we will try to finish this up, this transverse reinforcement criteria for the column as per IS 456. So this is it for today's lesson. We will see you in the next lesson. Thank you.